Welcome to this online lecture. In the last lecture, we have discussed the concept of partition into groups, where we have to partition of m and n elements, means m plus n elements, into two groups. Then it is given by m plus n factorial divided by m factorial into n factorial. After that, we have also discussed, or we can extend that the result to three groups. If m plus n plus p elements we have to divide into three groups, then it is given by the possibility of number of ways. It is given by m plus n plus p factorial divided by m factorial into n factorial into p factorial. Yes. Also, we have show you some remarks. If elements m, n and p, all these are same, then the result becomes or simplifies to just n factorial whole cube divided by 3 factorial into n factorial whole cube. Yes, that also we have discussed earlier. Now in this today's lecture, we will see here some examples on partition of a group. So let us see here the first example. In how many ways, just a minute, we will see another example first. In a school, 22 students wants to play cricket. A sport teacher decide to divide them into two teams, each consisting of 11 students. In how many different ways can this be done? So this is the example. I repeat again, or I will show you here. So see here. In a school, 22 students want to play cricket. A sport teachers decide to divide these 22 students into two teams, and each containing 11 students. So how many ways we can do this one? Yes. So here we have to divide, or you have to partition these 22 students into two teams. Yes. So you can recall your theorem. For m plus n elements are there, then you can partition into two groups, and it is given by m plus n factorial divided by m factorial into n factorial. Yes. So same theorem we have to apply for this example, and to determine the number of ways to divide these 22 students into two teams of 11 each. So we can apply the previous theorem, and hence the number of ways to partition these 22 students into two groups of 11 students, and it is given by 22 factorial divided by 11 factorial into 11 factorial. Just you can simplify this one, we get the answer. Yes. So I think, are you understand how we can solve this example by applying the previous theorem for partition of a group into two groups? Yes. Now let us see the second example. This one. A group of 12 students needs to be divided into two project teams, each consisting of 6 students. However, the teams are indistinguishable from one another, meaning is that the team have no specific label or names. Yes. So the question is, we have to find the different ways can this be done? Yes. So are you understand this example? Read it again. There are 12 students are given. We have to divide these 12 students into two project teams, and each project team contains 6 students. Yes. And another condition is given here. The teams are indistinguishable. What does it means? So in the last lecture we have discussed distinguishable case and indistinguishable case. Yes. So here the case is indistinguishable case is there. It means that the swapping of the two groups of 6 students do not create a new arrangement. Yes. And that's why you can write. So I will show here. So see here, Since the teams are indistinguishable, it means that the swapping of the two groups of 6 students do not create a new arrangement. Hence, we calculate the number of ways to divide the 12 students into two groups of 6 students without considering the indistinguishability. Yes, and it is given by number of students 12 factorial divided by 6 factorial into 6 factorial. So let's compute the factorial and we get the desired result. Yes. So see here the next theorem. In how many ways can 12 different flavored chocolates be distributed equally among 3 different children? So read again here the example. In how many ways can 12 different flavored chocolates be distributed equally among 3 different children? So to solve this problem, we first divide these 12 chocolates into how many groups? 12 chocolates into 3 different children, means you can divide it by 3. We get the 4 chocolates to each group. Yes, and hence the number of ways to do this considering the chocolates are distinct is given by 12 factorial divided by 4 factorial into 4 factorial into 4 factorial, and just you can compute the factorial of 12, 4 and just put here, we get your required answer. Yes. Now let us see here one result. This one. So the statement of this theorem is the number of ways to select the sum or all of n elements from a set is given by 2 raised to n minus 1. So are you understand here the meaning of this statement of this theorem? Number of ways to select sum or all of n elements from a set is given by, just we have to select all elements or some elements, and it is given by 2 raised to n minus 1, and this result we have to prove here. So for any set consider n elements, so each can either be included in a subset or not. Yes, and therefore for each of these n elements there are 2 choices. What are those? We have to include or we have to exclude. Yes, and hence the total number of subsets are 2 raised to n. So are you understand? There are, for n elements there are 2 choices, we have to include or exclude, and that's why the total number of subsets are 2 raised to n. And since we are interested in selecting some or all elements but not none, yes, and hence we can subtract it empty set. Are you understand? Just you can subtract it is 1, we get the desired result, it is 2 raised to n minus 1. Yes. Now we apply this result to one example. So let us see this one. Consider a set contains the 3 elements A, B, C, and the question is we have to select some or all of the elements from this set. So here this set contains 3 elements. So the number of ways to select some or all of the elements, you know that theorem is 2 raised to n minus 1. So here 2 raised to n is here 3 because 3 elements are in this set S. So 2 raised to cube minus 1. Yes. So this is the answer here. It is 7. So what are those subsets? If you have to find these subsets, what are those subsets? These 7 subsets. So see here. Just a minute. This one. A, B, C, A, B, A, C, B, C, A, B, C. So these are the 7 non-empty subsets that we can create by the given subset S, which contains the 3 elements A, B, C. Yes. So see here the next example. So this is the statement. The college development committee has 9 members. The principal of the college calls a meeting and invites one or more members. In how many different ways can the principal invite members to attend the meeting? So read again. So we will pause here for 10 seconds. Read this statement of this problem. So here the principal wants to call a meeting of college CDC or college development committee which contains 9 members, but he wants to call a meeting of 1 or more members. So how many ways we can do this one? So this is the example here. So the total number of subsets of this set with 9 elements is calculated by using 2 raised to 9. Yes, because here n is 9. 9 members means that set contains 9 elements. And since the principal invites 1 or more members, we exclude the empty set, and that's why 2 raised to 9 minus 1 is equals to 512 minus 1, and the answer is 511. Therefore, the principal can invite the members in 11 different ways. Yes. So let us see here the next example. In a music club, there are 7 different instruments available. The club president needs to select 1 or more instruments to be used in a concert. Yes. How many different selection can the president make? So this example is also parallel. Here n is 7. Just the total number of subsets of this set with 7 elements including empty set is 2 raised to 7. Yes, since the president must select at least 1 instrument and exclude the empty set, and it is given by 2 raised to 7 minus 1. So thus the president can make 127 different selection. Yes. So today's lecture we have solved 6 examples and a theorem on a partition of a group. Yes. So we will stop here.